I want to introduce you this routing protocol first, then I'll walk we all will walk through the presentations of OSPF later. I want to give you the overall view of OSPF, why it is so important, what are all features available in OSPF in the whiteboard. After which I'll take you through the pages of the presentation which I used to deliver. Now, every routing protocol is important. There is no protocol that this is old, this is later, this is latest, and this is updated, this is outdated. Nothing like that. Every routing protocol is good in in its area. Meaning, all routing protocols are not going to be good for you in all scenarios. Some scenarios will say OSPF is the best. For some scenario, RIP is the best. So there is no protocol small or big. All are important. Depending on our need, we pick one of the protocol. That's why we have these many routing protocols. We have OSPF, we have EIGF, we have RAPE, we have BGP, we have ISIS. Why we have all this? We also have the one protocol called OMP, Overlay Management Protocol. Anyway, you will not be learning this protocol because this protocol is only used in SD-WAN scenario. They get enabled dynamically. OMP get enabled dynamically. There is no routing protocol in SD-WAN you will enable for the SD-WAN fabric communication for the control plane. So we'll not study about OMP. Even if you are in SD-WAN class, you will not be learning how to enable OMP and all. They're already enabled. It's a routing protocol which gets enabled and works automatically. Let us not get into that now. What I'm trying to say is OSPF is also one of the routing protocol, like any other protocol. But OSPF is somewhat special. Every protocol is special in its own area. OSPF is special when it comes to a large network. OSPF is best when you have very big, large network. You don't know the size. The size is small, big, medium. Any big size, any small size, any medium size OSPF will fit in, but other protocols will not fit in to a very big size. That's the special of OSPF. OSPF can fit in small, medium, as well as big. If you take other protocols, they have limitation. EHRP will say a recommended is only 100 hop. I cannot support more than that. I can support, but don't expect me good quality. EHRP will say like that. RIP will say, no, I can only support up to 15 hops. Don't expect more than that from me. That is RIP's limitation. See, every protocol has got some limitation. This ISIS and OSPF has got no limit because both are link state routing protocol. That's the very first point. It's a link state routing protocol. See, we'll be learning about ISIS later, but that is also one of the link state routing protocol. ISIS is thought only in service provider track, but I'll still cover it in this track because we have mixed up people, some are service providers, some are enterprises. So later we'll learn that ISIS. But now I want to tell you that both ISIS and OSPF, they are link state routing protocol, meaning they depend on the link state advertisements to learn the topology. After learning the topology, using an algorithm called SPF, shortest path first, the protocol can finalize a path. So finalizing the best path is using this binary tree algorithm called shortest path first, which is also called as Dijkstra's algorithm. Dijkstra is the name of the person who proposed it. Now, link state routing protocol depends on link state advertisement. That's what I said. What is this link state advertisement? You see, wherever OSPF is running, those links which runs OSPF will advertise about the status of that port where the OSPF is running, the interface where the OSPF is running. See, that interface should have some bandwidth, right? So here, you're running OSPF on this link and this link, not on this link. In this link, maybe you don't run any protocol, but they're all active links. Links are active, but you run only OSPF. So what this OSPF running on this port will do, it will advertise to this port saying, hey, I'm having this network 10.0.0.0, mask is 8. You might have configured this IP 10.0.0.1. So from this, it copies the network portion. It says, hey, this is what my network, and the mask is 8. Very important. Mask also it will advertise. The mask is this, and the bandwidth on this link is it is F00, so it is 100 meg. For 100 meg, the auto cost is, let's say, 1. Cost is 1. This is what we call as link state advertisement. It advertises the status of the link, whether it is up or down. If it is up, what is the network on that link? And then what is the cost on that link? The link cost on that link, what is the cost? So that advertisement now goes through this to the other neighbor, which is here. So likewise, whatever the subnet that is available on this port, let's say this is F0/5, those things will be advertised through this wire so that this guy here can learn. Likewise, every router does this link state advertisement, but this is not the very first packet that goes. Understand? Because I'm starting from the word link state advertisement, don't think link state advertisement is the one which is going to discover the OSPF neighbors. No. I'm trying to explain you why OSPF is called as link state routing protocol. See, based on these informations that comes on the update, comes via this link state advertisement update. Based on this information that comes via this link state advertisement, like the subnet, the cost, the speed, 100 meg, the subnet mask, the MTU. Based on these information, which is going to be stored on every router's database called LSDB, link state database, the SPF algorithm can find one best path for each destination. So it is all collected in the link state database, which is used by the SPF algorithm to finalize the best path by comparing all the available paths for each destination. And the best path is going to be installed only in the routing table. You won't find the alternate paths in the routing table. In the routing table, you see only the best path, which is finalized by this SPF algorithm. That is why it is called as open shortest path first. SPF algorithm only finalizes the best path, which is there in the routing protocol routing table. And this SPF algorithm is an open standard protocol using which using which this routing protocol using which the routing protocol um, is designed. The routing protocol OSPF is designed by using this algorithm, which is already an open standard. Yep. So it's this routing protocol using sorry, it is this algorithm used by the routing protocol. That is why we call it is open shortest path first. OSPF is different, SPF is different. Understand? Some have got even this confusion. OSPF is open standard. SPF is also an open standard algorithm. Are they same? No. SPF is just an algorithm. It is not only used by routing protocol. It is also used by Microsoft, Intel, and all these places where Intel processor uses SPF algorithm to find out the registry values, the location, and then this one, Microsoft uses this to find out the location of the file on the hard disk. So SPF algorithm is used by various applications, even your navigator in your cell phone, the Google Maps, which we use to find some location, the path. They all use this algorithm SPF. Open shortest path first, OSPF, also uses the same algorithm. But this is a routing protocol. SPF is not a routing protocol. OSPF is a routing protocol. So Dijkstra did not prescribe a routing protocol. Dijkstra gave an algorithm which is right now used by various applications around the world, including this routing protocol. Fine. Now let us go back to this one. The link state advertisement, collectively called as link state update, which is collected by every router, and every router builds a database, and this database will be identical within an area. Very important point. If you take the database of router 1 and router 10 inside the same area, it will be identical. It will be same. Now, once the database is identical, what does that mean? It means that everyone knows about other routers' network. They're all in sync. Now, SPF algorithm using the database can find the best path by comparing all the available paths. And the best path is what given to the routing table manager, RIB. And the routing table manager will decide whether to keep OSPF path or not. See, OSPF is giving a route. What if I already have static route for that network? Then RIB will say I will not use OSPF. Why? Administrative distance of OSPF is 110. Static route distance, static route's administrative distance is only 1. So lower the administrative distance, more weightage, more preference. So it is the final authority. Who? RIB. RIB is the final authoritative algorithm to decide who will be there in the, which route will be there in the routing table. Now, this is the reason why we call OSPF as a link state routing protocol. It fully depends on the link state advertisement alone, not any other route updates. Is link state advertisement a route update? No. It's not a route update. You see, I'm in this location. This is where airport is. And here I am. And there is also another road like this. There is also another road like this. There are many roads. There are many roads. Now, we got various paths to reach airport. If someone will tell me, I'm here. I'm here. Someone is going to tell me, hey, if you want to go to airport, take this path. Then it cannot be a link state routing protocol. Because this guy told me, I know a path. I have to go straight, take right, and then take left. This guy is telling me. And he also said, for me it is 10 kilometer. Then me here, what I do is I listen to this one and I say, okay, for you 10 kilometer, between you and me is 2 kilometers, so for me it is 12 kilometer. I will go like this. This is not link state routing protocol. If a router will learn route like this, it is a distance vector routing protocol. RIP, routing information protocol, EIGRP, enhanced interior gateway routing protocol, they all work like this only. What? Neighbor will say, for me 10 kilometer. Then what I'll say, for you 10 kilometer. Then between you and me 2 kilometers. So for me it is totally 12 kilometers. And this guy will say, hey, for me 15 kilometer. Then I'll calculate for between you and me is 15 plus 1 plus 2. It is 18 kilometer. Then I'll not go through this path because this is 18 kilometer. This is 12 kilometer. I'll go this way. You see, this is what a distance vector protocol will do. Distance vector protocols learn route from the neighbor, either partially or fully. Partially or fully, they learn the route and the metric from the neighbor. Whereas OSPF learns only the link state advertisement, not the route. See, if a neighbor is giving a route, from where it is coming? From where the neighbor will give the route? From the routing table. What do you have in the routing table? Only the best routes. So if a neighbor is advertising only the best route to me, I can learn only partial topology. Because he's advertising only the best route to me. He's advertising only his best route. So will I be able to learn the complete topology? Not possible. When a neighbor advertises in EIGRP and in RIP, it advertises only the best route. Where is the best route? In the routing table. Only those routes are given to me. When I take that as the update, route update, am I learning complete topology? No, because my neighbor did not advertise the route which are not best for him. Whereas in OSPF, every router, these dots are routers, okay? Every router, they keep advertising, they advertise. Every router advertises their link and their status, link state. They advertise the link state. This link state makes every router to learn the complete topology. Then maybe another link here. Another link here. You know, link state protocol will help every router to know this topology. This topology will be seen in each router, the complete topology, so that by running the SPF algorithm, it can find the low cost path by itself. So the route picking up is by comparing the cost on each path to the airport. Cost on each path, the total cost. For example, let's say for each link a cost is 1. So here 1, here 1, here 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. If the cost on the link is 1, assume, when will be the cost be 1? If it is 100 meg, it is 1. So now, if I go this route, cost is 1 plus 1 plus 1, 3. If I take this route, then it is 1 plus 1 plus, here 1 plus 1, 4. If I take this route, then it is 1 plus 1 plus 1 plus 1 is 4, 5, 6, 7, 8, 9, 10. The green route is 10. See, all these informations will be there in the link state database. Now the link state database will compare and say, hey, this is the smallest. I'm going to use the red route. In case if the red route fails, I'll go with the gray route because it is 4. And then likewise, in the database, it will have all possible paths for each destination. Here I have only one destination, airport. There may be many networks in your topology. For each network, all possible paths along with the best path will be seen in the link state database. In the routing table, you will have only the best route. Now, what is the advantage of this link state routing protocol? The advantage is if the primary path goes down, if this path with the cost 3 goes down, immediately, without waiting for anyone's response, it can decide by itself the second path. Immediately, it will go to the database. Okay, now I'll use this path because the first path with the low cost is gone. Let me use the next path. It won't take much time. So, in short, what I want to say is the fastest convergence protocol, the fastest is EIGRP. Sorry, OSPF. OSPF is the fastest converging protocol. See, some people will say EIGRP is fast convergence. That is very, very wrong. You see, what they say, EIGRP will send a hello packet every 5 seconds, and the timer is 15 seconds. Whereas OSPF sends hello packet only every 10 seconds, and the dead timer is 40 seconds. So, what these people think is this is dead time, okay? This is hello. What they think is, look at this. This is only 15 seconds. In 15 seconds, it can decide one neighbor is dead, but OSPF takes 40 seconds to decide a neighbor is dead. If a neighbor is not sending hello for 40 seconds, only then OSPF can take a decision. But EIGRP can decide in 15 seconds. So EIGRP is fast in convergence. This is what they imagine. That's not in the book. That's their assumption. You need to understand one thing. This timer is only to decide whether the neighbor is dead or not. That is not going to impact the convergence. Convergence is impacted based on the updates, quick updates. In both, we have triggered update. Whenever there is a change, immediately the change will be shooted to everyone. It is both in EIGRP as well as in OSPF. Yeah. So it is no way connected to convergence. Convergence is based on the update. As soon as some link goes down, immediately an update comes and says the link is gone down. Now, if it is OSPF, what it will do, then it will look into the database and take the other path via other link. That is fast convergence. If it is EIGRP, when a update comes and says the link is down, EIGRP will go and check the topology table. If the root is found, it will use. If the root is not found, EIGRP will send a query and wait for query response, which is a time-consuming one. OSPF no need to send any query because OSPF have got the complete topology. EIGRP, though it has got topology table, it is not complete. Why? Because it learned route from neighbor. Neighbor will send only the best route. EIGRP cannot have the complete topology table. So it goes and now asks everyone for any alternate path. And then when someone responds, it will use it. It is time consuming. OSPF is the fast converging routing protocol because it knows the complete map. If one road is blocked, it will take the another road. See, EIGRP is like we in foreign country. Even though we work in foreign country, we don't know all routes like a native guy. Native people will know all the routes. We know one or two routes to reach office. If the primary route goes down, we go through the secondary route. What if there is no secondary route? Then you will start querying someone in the maybe online or in the road. You'll call some friends and ask, hey, the usual road that I come to office is blocked. What can I do? Then if he's a local guy, he knows. every path. He's going to ask you where you are right now. What do you see in your left and right? Then you will say the location. Fine, you need to take a right and then come this way. So he can tell you exactly what path you need to take because he is a OSPF. He has got the complete map of the city. He is born and brought up in that area. He knows the complete topology. So he can take a fine-tuned path selection. No protocols can do that fine-tuned path selection. Like a foreigner cannot take the shortest path. He knows only one or two paths as shortest. He keeps going with that path. If that path is gone, finish. He don't know anything. He has to query someone, wait for someone to respond. So is this a fast convergence? No. He has to wait. He cannot press the accelerator till someone updates him with a new path. But OSPF can immediately press the accelerator because it knows the alternate path in the topology table in the link state database. Okay, this link goes down. Okay, that also goes down, no problem. Now the other path, I know all the paths. So fast convergence protocol. OSPF is the fastest convergence protocol. This is just a timer to decide whether the neighbor is dead or not. To throw the neighbor out from the neighbor table, this timer is used. Next. OSPF is a link state routing protocol, which makes OSPF a special protocol. The administrative distance of OSPF is 110. What is administrative distance? It's the numerical value that is given by Cisco to this OSPF. It's a numerical value. It is a numerical value given by Cisco. It's not industry standard, understand? It's a numerical value given by Cisco to OSPF. This number defines the weightage to this protocol. See, if I run EIGRP in Cisco router, also OSPF in Cisco router, EIGRP is preferred. Why? Because it's a Cisco's protocol. Cisco has given more weightage to it. You know how? For EIGRP, they have given 90 as a number. Smaller the administrative distance, lower the administrative distance, more weightage. So they want to prefer their protocol, so they have given 90, and for OSPF they have given 110. Smaller the number, more preference is given to those routes by the routing protocol. Whereas the other vendors, they don't have the same level of prioritization, the preference level. Every vendor has got their own number, okay? Every vendor has got their own number. So that's why I said Cisco has given this number, 110. Don't expect this 110 in every vendor. I have seen some vendor having 25 for OSPF. And that vendor never supports EIGRP. Okay, so this is Cisco's preference to OSPF. When RIP is enabled on the router, OSPF is also running on the router. When both RIP and OSPF gives the path information for a destination, in that case OSPF is preferred because RIP's administrative distance is 120. So the router is going to ignore RIP's recommendation, ignore RIP's path preference, and give importance to OSPF path preference. All right. So this is to tell the routing protocol How important is this protocol? Sorry, it is to tell the routing table algorithm called RIB how important is this protocol's update. All right, now we got OSPF, administrative distance length. We know the shortest path first. We know why it is called as link state routing protocol. We know about the link state database. It's like a topology table, and the topology table will be same for all the routers in this area. See, in OSPF we have multiple areas. Within an area, you can expect all the routers to have identical database. Yeah. So within India, everyone is going to have same map, India map. But go to Afghanistan and check India map. It will be different. Go to Pakistan and check India map. It will be different. It won't be identical. Meaning, in India, you need to know every states and union territories. So all information will be very clearly given in the Indian map here for Indians. But for people in Kabul, they need to know only the states of Afghanistan. So India map in Kabul will have only the outline. You will not see Tamil Nadu, Kerala, Karnataka, Andhra, Uttar Pradesh, Bihar, West Bengal. Nothing you can see. You will see outline India thing, let's say. But when you see Afghanistan, you will see every single district, states of Afghanistan. So the detailed information of an area is only needed for that area member. The other area member no need a detailed information. They want only the summary information. Understand this. The reason why within an area the topology table is identical. Why it is not identical with other area? Because the other area members no need the detailed info. They need only the summary. I want to buy a walnut. Walnut is grown in Afghanistan in plenty. Like groundnut in India, walnut is grown in Afghanistan in plenty. So I need to know, okay, I need it is available in Afghanistan. That's all I need to know. Sitting in India, I need to know that it is available in Afghanistan. So that I'll check some Afghanistan websites and I can order for walnut. But being in India, if I want to buy groundnut, I want to know exactly in which location in India it is grown much so that I can go directly buy myself. No need to depend on courier and online purchase. No visa needed, so I can go directly. I can drive myself, buy. For that, I need to know a detailed map. Likewise, within an area, if you have detailed information, you can take the best and shortest and more accurate path. But going to other area network, you need to know only the ABR, the border. From border, that area routers will take care. So you no need to know about every small subnets and location of area, the network in the other area. Not necessary. So it is good that they made this identical database only within an area. Yep. So don't expect the link state database to be identical between routers that are in different area. That's the important point. Next is, when we talk about area, first of all, we need to know why we need areas. Why is areas important? Why do we need area? Multiple areas. See, when we have multiple areas, we get a lot of advantages. Like, the problem that is in an area will not impact the other area. Yeah, the problem in one area will not impact the other area. Or it is easy to troubleshoot. For example, unfortunately, we had a very big earthquake in Turkey, which no one expected, but it happened. Now, because it is bordered, because it is Turkey and Syria, you can extend your help easily. If you don't have the division, if there is no countries, if there is no continents, then how you will extend your help? To whom you will extend your help? No idea, because it's one big nation. There is no countries. If there is no boundaries, it's difficult to extend our help. Because it has got boundaries, okay, talk to Syria, talk to Turkey, and extend your help. Finish. So troubleshooting is easy. Maintenance is easy. So areas, dividing the big topology into small areas helps to manage easily, troubleshoot easily. Fine. So let us draw a diagram and then understand this area. I have we have a router here, the borders, and this is what called as ABR, area border router. This area border router is the only router that I need to know if I want to go to anywhere in this blue. I need not to know the complete details of the locations and the networks of blue. All that I need to know is to go to that blue, network, I need to go to area border router. I need to go to my border. That's all I need to know. Why should I know the complete topology of this blue? Not necessary. And so on the blue. Even the blue guys no need to know the details of the orange in the left. That makes the routers in this area to have a simplified routing table. So you see now you no need to know the detailed network subnets of other area. As a result, the routing table of this area will be small. You have only detailed information of your own area, network. For the other area, you will have only the summary route. For example, just for your understanding, 10.1 subnets are here. 10.2.10.3. Now, here I no need to learn all those precise route. I need to simply say anything that starts with 10, just go to ABR. Send the packet to ABR. This ABR will have information saying anything that starts with 10, you need to go to this area border route. And when the packet goes to this area border router, then it will have a very clear subnetted route information. For example, if packet is 10.1, 10.3.1.1, this is where the packet wants to go. Whether it is 10.3 or 10.2 or 10.1, this is the only route that will be matched and sent here. And this will also use that same 10.0.0.0, go to this ABR1. So it will send the packet to ABR1. From ABR2, it goes to ABR1. Just one route in the routing table for all these subnetted networks. With that one single route, it can go to A1. And in A1, it will go and check for 10.3 and it sends the packet to 10.3. Only A1 knows about every single subnet. A2 knows only the summary of all the subnet. Let's say you have 10.255.0.0/16. So instead of learning 255 routes, you just got only one route 10.0.0.0 in both ABR as well as on the internal router. So this makes the routing table simple, smaller. This is another reason why the topology table, the database, will not be identical, because we summarize. Now tell me, if you don't have areas, is there any chance to do this neat, hygienic summarization? Not possible. Because of these areas, you are able to do summarization. If no areas, you will not have summarization point. Because you have multiple areas, you got ABR. So for all this network, I'll do summarization here. ABR is the summarization point for all the area network, subnetted network. I do summarization and I send only the summary route to this backbone router. This is what called as backbone router. Why? Because this area is what called as backbone area. What is backbone area? The backbone area is the one which acts as a connection point, acts as a transit between non-backbone areas. See, the OSPF is designed in this way. It is designed to advertise the route from one area, let's say area 100. It is designed to advertise the area 100 routes only to area 0. It cannot advertise to area 200 directly. Likewise, area 200 also cannot. Area 200 also cannot advertise the route directly to area 100. OSPF is designed only to hand over to area 0. Area 0, the number 0 is what reserved for backbone. Right, backbone area is the only one which will talk to non-backbone areas. So only through backbone area 100 summary route is passed on to area 200. Likewise, area 200's summary route passed on to area 100 through this backbone area. So without area 0, can OSPF share the routes between one area to another? Not possible. Not at all possible. OSPF cannot advertise a route of an area to another area without help of area 0. Not possible. Even if you have a router here and here connected back to back, no route advertisement will go through this way. And in another, I want to tell you something, not even route advertisement, they won't even form neighbor like this. This belong to area 100. This belong to area 200. They won't form neighbor in first place. Area ID must match in order to form neighbor. So there is no neighborship between these two, which means you cannot share anything. How can you share without neighborship? First neighborship. That is what I started in the beginning. Don't think, LSAs are the one which is going to discover the packet. Discovery of neighbor is through the hello packets. In that hello packet, no link state advertisement will go. In the hello packets, you will have only the neighbor list, not the link state advertisement. Hello packets are to discover neighbor. After finding a neighbor, the adjacency is made by sharing the link state advertisement called DBD, database distribution, DBD, which is a summary of LSDB, which we will be talking later after some time. Now, coming back to the story, this neighborship, if it needs to come, the hello packet that goes from this side and this side must have the same area ID, but they don't have here same area ID. They cannot form neighbor. Now, if I have area 0 instead of area 200, will they form neighbor? Even now they cannot form neighbor. Then how it should be? It should be like this. One side link is area 100. On the same router, the other side link should be area 0. Only then the route from 100 will be placed into area 0. This is what we call as ABR router. ABR router has got one connection to area 0. At least one connection to area 0. Only then it can be called as ABR router. So only an ABR router can take routes from other area and keep it in area 0 so that through area 0 it will reach the other areas. Kindly ask me question. Is the class going good?
So in that area border router, that area 0 interface, under that interface we have to allow this network.
No, don't worry about allowing. You are not going to allow. OSP will allow it, advertise it. You are going to simply advertise it.
Yeah, we have to advertise it in that interface.
No. You don't advertise it on that interface. OSP will take and advertise it on that interface. You are going to simply advertise. You're going to simply tell OSPF to run on those links. That's all. We are not going to say, you these routes, take that link. No. We are not going to do that static job. This is a dynamic routing protocol. So OSP will do that job. OSP will say which network should be advertised via which link. We will simply run OSPF on those links.
Okay.
Any other question, please?
No.
Mr. Rahman, are you there? Any question?
No, see, thank you.
All right. So The administrative distance is configurable. Even though Cisco has given 110 to prefer OSPF as a preference level, if you wish OSPF to have lower number like 10, 20, you can say 10, administrative distance 10, so that it can be prioritized more than EIGRP, because EIGRP is the only one according to Cisco. EIGRP is the only one which has got administrative distance of 90, and for summary route it is administrative distance of 5. EIGRP is the only one which has got this lower administrative distance because it is Cisco's router. They have kept the lowest one, and if you want, you can go and change it. That's what Cisco says. See, this is our router, our protocol. We keep it like this, preferring our protocol in our router. But if you don't like, if you want BGP, you can very well go and say BGP administrative distance 4, BGP administrative distance 5. You can say that. No one is going to stop us from doing that. Okay. Next. As we saw earlier, the hello packets, which is sent every 10 seconds, is the reason for neighbor discovery. Hello goes from this router to that router to this router, so both routers now know each other. Now, to which address the hello packets are sent? There is an address called 224.0.0.5. This is the multicast address OSPF uses to send hello packets. Why is there a need for a multicast address? Because you don't know the neighbor. Because you don't know the neighbor, you need to do multicasting. If I know my neighbor, I can straight away go and handshake with him. I can go and form neighborship with him. But when I don't know my neighbor, I need to talk to the group to know my neighbor. I have to talk to the group to know my neighbor. All the running OSPF routers, all the routers that runs OSPF will be listening to this address. So when you send a hello packet to this address, all those listening routers will learn about you, about your router ID, about your source address from where the hello packet is coming, and started comparing the parameters. And if all these parameters are going okay, like area ID matching on either side, timer matching on it, then they accept as neighbor. The multicast address 224.0.0.5 is what used every 10 seconds to send hello packets. Don't think that after discovering neighbor, it will do unicast. Never. Even after forming neighbor, the hello packets are sent only to this multicast address every 10 seconds. What is the advantage? Advantage is if I have 10 neighbors, I don't need to send 10 packets. I just send only one packet, and all 10 neighbors will know I'm alive. See, I need to send a hello packet every 10 seconds. Even after forming neighbor, I need to send the hello packet every 10 seconds to say I'm alive. That is what periodically going to refresh my neighborship. If I have multiple neighbors, instead of sending the hello packets to each neighbor saying I'm alive, I'm not dead, Instead of saying that individually, you can send it to the multicast address and everyone will know that you are alive. All right. So it's like a radio broadcast. You you take one frequency which is talking only to your village people, and you say, "Hey, I am alive." Then everyone in the village has heard you. You don't need to call every single person in this village to say you are alive. It's multicast address. It is the same multicast address using which the updates are sent, but some updates are query and response. That will be unicast, which we'll talk later. But most of the time you'll see multicast address 224005 used. And if the neighbor is not sending hello for 40 seconds, the neighbor is considered as dead. So how many times bigger the dead timer? It is 40 seconds. And this is common. This timer is common because most of us work on the LAN environment with OSPF. Very rarely we will have a WAN environment like frame relay. You might have heard about this or might not. That doesn't matter. See, there's a WAN technology called frame relay, using which you are trying to bridge between your data center 1 and data center 2 using OSPF. So you are using OSPF to bridge these two data centers. These two data centers belong to your company, but they are in different location. Because of this, you want to have a frame relay cloud in the middle to connect between these two. If you will choose OSPF as a protocol to advertise the data center 1 route to data center 2 and vice versa, then you need a different OSPF. I mean, different timer. The reason is frame relay itself is very costly. And if you're going to send a hello packet every 10 seconds in this frame relay link, the bandwidth will be now highly utilized by by OSPF, which is going to increase your cost. So to avoid this increase of cost, OSPF is by default on a WAN environment. This is what called as WAN environment, where NBMA, non-broadcast multi-access, NBMA. We call this as WAN environment. In this WAN environment, the timer is 30 and 120. Instead of sending every 10 seconds, you send only every 30 seconds a hello packet. So you have reduced the timer 3 times. The frequency is only every 30 seconds. So you have reduced 2 packets now. 2 cycles you have reduced in 30 seconds. Same way, dead timer is also 4 times of hello packet. 4 times of hello. 10 means 40. 30 means 120. Which is good actually. But if you wish to change it, you can change it. But very important is you need to change it on both. Otherwise, the neighborship won't come. If you're in WAN environment, then you have to change it on this router as well as this router. If you are in LAN environment, the timer is 10 and 40. You have to change it on this router as well as on this router. The timer need to match. Because the timer is sent in the hello packet, the hello packets will be compared, and only when the timer is matched, the neighborship comes. Yeah? Timer need to match. So we saw about a multicast address. We also saw why do we need area. When you have multiple areas, you get a summarization point. The router where you do summarization is a summarization point. Which one is a summarization point? ABR. You cannot do summarization anywhere. You can do only summarization on ABR. That's a summarization point. That's the first advantage of having multiple areas. Secondly, because you do summarization, you avoid sending detailed subnet, which is reducing the bandwidth utilization and process utilization, as well as the buffer utilization on the receiving router. So the memory is less consumed, bandwidth is consumed less, process is also less. You don't send too many updates. Too many updates, too many process. Yeah. So too many process is going to increase the time taken for packet forwarding. So it's good. Summarization is good, but the summarization is not dynamically done, not by default. Summarization. Summarization need to be done manually. There is no automatic summarization. See, in the older version of EIGRP and in the current version of RIP, you have auto summarization. Auto summarization. In OSPF, manual summarization always. You need to go to the ABR router and say summarize all this area 100 networks using a command called range command, area 100 range. So summarization is done on ABR. That's why it is called a summarization point. You cannot do summarization on anywhere else. You cannot do summarization on this router or this router. No. For this area, this is the summarization point. For this area, this is the summarization point. So you cannot do summarization here and there, wherever. The other protocols, they don't have this discipline. The other protocols, they don't have this proper approach. Anywhere you like, you can do summarization. There is no defined place. But in OSPF, you see, you cannot do summarization anywhere, only on ABR. And it is very neat and hygienic. It's really a very good approach. If you don't have areas, you will not have ABR. If you don't have ABR, you will not have summarization point. Secondly, if a network goes down, for example, this particular network 10.3.00 is gone down. Because I have done summarization, this information about this network going down, this notification will not go to area 0 or any other area. It won't go to area 0. In turn, it will not go to any other area. It will, the impact will be there only on this area. Any change in this topology, the notification will be sent only to this area members. As a result, the other areas are not getting disturbed for these small changes. This change may not, this change is not relevant. This change, the update about this change is not that important for other areas. I gave walnut is grown much in Afghanistan as an example. There is a shop and that shop is closed today in Afghanistan. Is it so important for me in India? No. If a shop in Afghanistan which sells walnut is closed, that is not a good, that is not really an important update for me. If someone says in entire Afghanistan walnut is finished, then it is an update. One walnut shop closing is not a real useful update for me. It is a waste of time. If someone is sending me, calling me, uh, Jay, you know what happened? That shop where we went that day when you came to Kabul, that shop is closed today. If he calls and tells me that, what is the use? No use. There are many other shops. And it's not needed. I'm not interested in buying walnut today. It's not needed for me. So why that advertisement? One small network which I rarely communicate. Very rarely I communicate. If that goes down, if the update comes and changes my routing table, it's a disturbance to me. That's not really a useful update. So in short, what I want to say is, in order to localize the impact of the change in this area, in order to localize the impact of the change in this area, localize it, you need area. If you don't have multiple area, if all are in one big cluster, then the impact will be bad. Whatever changes here will impact everyone. Then I will get call every second. I will get call. In Istanbul, that shop is closed. You cannot buy saffron. In Syria, that shop is closed, so you cannot buy saffron there also. In Egypt also it is closed. In Afghanistan, a new shop opened for saffron. Yeah, who wants that? I don't want to buy saffron today. See, that's the problem if all are in one big area. When you have small areas, summarization is done. So whatever the change that happens in one area cannot impact other area members as a result. Within an area, the routes are getting updated as per the new change, but the other areas still uh, have the same routing table. Their routing table is not disturbed with this silly changes that happens in other area. So first thing is we got a summarization point because of area. Secondly, we can localize the impact of topology change within an area because of this area. In turn, we don't disturb the other areas, so process utilization by OSPF is reduced. Bandwidth utilization by OSPF is reduced because we summarize, so on. So this is a big advantage. Frequent talkers. Frequent talkers, what is that? All those devices that are in the network which frequently communicate. You will put them in an area. All the frequent talkers are grouped in one area. department wise. They are in different areas. Frequent talker of HR department, they are in one area. Frequent talker of front office is another area. So they don't have a business to talk every minute to other department. So you can put them in different areas, which is good. And if they want to communicate from one area to another, they use a summary route, come through area 0 to communicate. Today for our discussion, last topic is this: OSPF adjacency. See, even though I'm teaching you here in the whiteboard, I will also be teaching the same topic with a presentation, but little faster there. So that with the idea of what we have learned here, we can quickly go through those pictures and wordings that Siska has put there, and we can finish fast. When I start with presentation, what happens is every now and then in the middle, I need to jump to the whiteboard to make you understand this. So let me finish all the whiteboard and then take you to the presentation. You will be able to relate. OSPF adjacency. Adjacency, peering, neighborship, all sound similar. But forming neighbor is half a way to form adjacency. So after forming neighbor, we also do something more, not simply discovering neighbor and stopping. If you see someone coming and talking to us, they're not talking to us just because you are so sweet and they want something from us. So they will come and say hi, hello, and then they will start. What they are looking for, no? That is what called as adjacency. Hi, hello, and if he goes, then he's forming neighbor. That's all. I know him. He's there only for 10 years. I see him. He used to say hi in the road. But that is not real adjacency. Adjacency is like we sit and talk and share all the experience so that whichever the things that I can do, he can take from me the help. Likewise, whatever he can do for me, I take his help. That is adjacency. In OSPF also, this level of forming neighborship, the structure, the step-by-step states, neighborship adjacency states is seen. First of all, when a router is configured with OSPF, that router will send a hello packet with its own router ID 1.1.1. This guy's router ID is 2.2.2. What is the router ID? It's an address that will be used to identify the router in OSPF realm. This address is not necessary address on the interface. This can be just an address, a 32-bit number in an IPv4 format. This need not to be a reachable IP address. This is not a reachable IP address. The reachable IP address between these two is 10.0.0.1, 10.0.0.2 on this F00. This one may be on an interface loopback, Maybe not at all in any interface. Not necessary to be on the interface. So here router A is using its router ID saying, hey, I am 1111 coming from 10.0.0.1. We call this as hello packet. As I said earlier, it will be sent to 224.0.0.5. And this is what we called as init state packet. Init state packet. Init state packet going from A to B. Now B is responding back. Or B gets its turn. We should not call it as a response packet always. Sometimes it is not a response packet. B gets a turn to say hello. This is a hello packet. Sometimes it will be also a response with unicast. Sometimes it is also a broadcast, which means it's normal hello coming from B. Now B has already learned a neighbor called 11111. Now when router B sends the hello packet, it will also send the neighbor list in the hello packet. And router 2 receiving this hello packet, it understands that, aha, router B already know me, now I know him. Now I know him and he already know me. How router 2 knows that he already know me? Because in the neighbor list, router A can see its own address coming from B. This is the neighbor list of B. So router A learns that I got a neighbor from 10.0.0.2 and the neighbor name is 2.2.2.2. And router B knows that I have a neighbor 10.0.0.1 whose router ID is 1111. We call this as two-way state. After two-way state, what happens? From the hello packet, these two routers compare to decide on the master role. See, one should be a master, one should be a slave here. For that, they compare the hello packets that is coming. That place where they do the comparison, they both compare. We call it as X start state. They both compare the router IDs. And router A says, my router ID is smaller. Router B says, mine is bigger, 2222. So I am going to be the master. I'm going to be the master. And you're going to be the slave. And router A says, yes, we are slaves. This decision making is what called as X-start state. Say I have only two routers, it's point-to-point network. In point-to-point network, one will be elected as master, the other one will be slave. Based on the router ID they decide. In point-to-point network, the priority is not at all in consideration. Not at all considered. Right. So In extant state, one becomes master, the other one becomes slave. What is that they are going to do with this role? They're going to start the exchange of route updates. So now the master will initiate the exchange. Only a master can initiate the exchange. The master is sending the updates that it has got, the link state advertisements. This is where the link state advertisement comes into picture. LSUs and things like that. So we call it as DBD, database description. This DBD is exchanged and we call the state as loading state, sorry, exchange state. In the exchange state, the master first initiates the exchange and the slave now exchanges with acknowledgement. Acknowledgement for what? Acknowledgement for what it has received. DBD. So master slave, they have exchanged their DBD now. We call it as exchange state. I already written here, anyway I'm writing here. The next state is loading state. Comes again in between these two. What is loading state? The query and response. See, because it is only DBD shared. What is DBD? It's a summary, it's in a nutshell. They are sharing the database. The database is too big. Here only the summary, a nutshell, very short description about the database is exchanged. So there will be some queries between them to ask. They ask some queries and we call it as the LSR, link state request. For that the response comes, which is LSU. LSR and LSU. So this happens between these two routers. We call this as loading state. Once this loading state is completed, which means there is no query to ask, they are all fully synchronized. It reaches the final state called full state. This is what you will find when a neighbor is discovered. We used to see a log saying loading to full. What does this mean? It means that it has gone to this fully synchronized state of relationship with the router. Any question? The state, right from down state to initially it was nothing down, and then initial state, two-way state, exchange state, extart state, exchange state, loading state, and full state. Anyone has got any question? Please ask.
The packet type will be described in the next class, right? The packets.
Yeah, we'll capture and see all these packets. Packet type is different. Packet type is totally different from what we have learned. Here we are seeing adjacency types. Message types like packet types, hello packets, DBD, LSR, LSU, acknowledgement, LSAC. We'll discuss that in the Wireshark, with the Wireshark. We'll capture the real conversations and we'll discuss what is going inside. We'll see that next class. Any other question? Question, please.
No, sir.
No question. Find the answer to